Okay, everyone. Today we're going to hear from Shota Komatsu from CERN on the Worldsheet G function and AdS CFT. Thank you, Shota.
Okay, thanks for the invitation. And so yes, today I'm going to talk about some works about AdS CFT, and in particular the application of what's called G function to the n equals 4 super Mill theory, which is a canonical example of AdS CFT correspondence. And the talk is based on two papers, mostly based on two papers that I wrote already 2 years ago. But there are several follow-up papers, and I am going to mention some follow-ups as well. Okay, so let me just first state the goal and two very clearly in the beginning of the talk. So the goal of the talk is to compute some correlation functions in planar large n equals 4 super mills at finite Hooft coupling. And the two we are using, I'm using is at weak coupling of n equals 4 super mills. We use some kind of collective field approach, and that has nice connection to the techniques people develop in the matrix model. And at finite coupling, we use the method called integrability. And here you see the relation to what's called G function. So let me just begin with the introduction. So I think everyone agrees that holography has been a great source of insight. And for instance, a strongly coupled quantum field theory, we can analyze it using AdS CFT correspondence using the classical gravity, and examples are like AdS QCD or AdS condensed matter. And alternatively, we can try to understand quantum gravity from conformal field theory or quantum field theory. And there are several examples like black hole microstate counting and the recent resolution of information paradox, which by itself doesn't rely on AdS CFT, but it certainly got some inspiration from AdS CFT correspondence. And however, I should say that there have been remarkable progress, but ultimately we'd really like to understand precisely how quantum gravity emerges from quantum field theory or vice versa. And one particular question one might want to answer in this context is how to see the bulk from the boundary. And of course, there have been various important progress, especially in recent years, using the idea from quantum information, such as quantum error correction, tensor network, or the Ryuta-Kanagi formula, which explicitly relates the entanglement entropy on the boundary theory to some area of the surface in the bulk. But still, I should say there are many unanswered questions. For example, we still don't have a very, very sharp answer to the question, how does the bulk locality emerges from the boundary? Especially if you take the limit when the gravity becomes almost classical, there is an approximate notion of locality in the bulk. And there are some development of understanding, but we don't have a very sharp answer to this question. And much more difficult question is how do we describe the interior of the black holes? And so given that there are many unanswered questions, it might be fruitful to study some solvable toy models. And the toy models are useful, and the philosophy, at least I would advocate, is that philosophy is that, of course, I think the core or the best part of physics is, I would say, like a good approximation. Like if you really understand what kind of physics is going on, then you can come up with nice approximation, and then you can study realistical systems using that approximation. But the philosophy here that I would advocate is that if you don't understand a problem, sometimes it's actually useful to solve it exactly. And once you have an exact solution, you can often learn more than expected from the exact solutions. So this might not be the most canonical way of thinking about the toy models, but that's the way I think about the toy models. So I guess one example is Landau's theory of phase transition versus exact solutions to the Ising model. I think I heard that before there have been exact solutions to the 2D Ising model. Some people are even skeptical about the existence of the phase transition. But having exact solution, you can study everything very, very concretely. And in fact, of course, people have explore that possibility in AdS CFT or holography as well. And there are several known examples of solvable holography. And I just listed the 3 of them, which were recently studied. And the first one is ON vector model, which is known to be due to what's called like a Vasiliev higher spin gravity theory. And another one, which has been attracting a lot of attention recently, is symmetrical bifold CFT2, which is supposed to be due to tensionless string in AdS3 spacetime. And also, like recently, a lot of efforts has been put in the study of duality between matrix model and 2-dimensional Jacquier-type volume gravity. However, one drawback of these solvable toy models are that most of them are far from Einstein gravity. For instance, these example, higher spin gravity and tensionless string have infinitely many massless fields. And some of these examples are lower dimensional. And because of that, they are topological. The gravity is topological. And one example in which we can really make contact with usual gravity, but still might be solvable, is n equals 4 super-Mills in 4 dimensions, which I'm going to talk about today. And so just to remind you that n equals 4 super-Mills in 4 dimensions is a canonical example of the AdS CFT correspondence. And the duality relates the n equals 4 super-Mills to the superstring on AdS prime times S pi background. And these are basic dictionary between these 2 theories. And first of all, the rank of the gauge group, inverse of the rank of the gauge group becomes roughly the Newton constant on the gravity side, which is also related to the string coupling, which basically governs the rate at which a string splits into 2 or 2 strings joins into 1. And another parameter in n equals 4 super-Mills, which is the so-called Hooft coupling, which is defined in this way, is related to the string tension. And if you increase the string tension, then this string becomes point-like, and therefore all massive modes becomes infinitely heavy because the tension becomes very large. Then the theory reduces to a theory of point-like object, which is nothing but the supergravity. So in this regime, we can really hope to make contact with the usual gravity description, although supersymmetry is there. However, this also shows that in order to really go to the supergravity regime, we really need some non-perturbative approach to analyze this n equals 4 super-Mills. And the non-perturbative approach that would allow us to analyze this regime is precisely integrability, which is the main subject of the talk today. Okay, so let's just review the integrability story in n equals 4 super-Mills. So in the large n limit, n equals 4 super-Mills is believed to be solvable. And this was first found by Minahan and Zarembo in 2002, which is already 20 years ago. And they basically studied a composite operator, which is called single trace operator. So basically what they did is to consider a product of scalar field, complex scalar fields in n equals 4 super-Mills at the same position. And if you take a trace, then this defines you the gauge invariant operator. And they analyzed the one loop anomalous dimension of this single trace operator. Because all the fields are at the coincident points, they develop anomalous dimension. And what they found is interesting. So they basically found that if you map this sequence of fields, Z and X, to a kind of a sequence of spin by mapping Z to upspin and X to downspin, then you can actually map the one loop dilatation operator to this spin chain Hamiltonian, which is the most basic spin chain Hamiltonian you would write down, which is called Heisenberg spin chain. And under this mapping, this one loop computation of anomalous dimension reduces the computation of the spin chain, the energy of the spin chain state. And what was remarkable is that this Heisenberg Hamiltonian turns out to have a nice property called integrability, and you can solve it by what's called Bethe ansatz. So what is Bethe ansatz? Let me just explain in the simplest example. So Bethe ansatz is basically a way to construct the eigenstate of this Hamiltonian by first writing down ansatz and fixing some parameters. So the step one, you just write ansatz. So basically the idea is to view the downspin as an excitation and upspin as a vacuum. And then you write an ansatz for this wave function. And this wave function is extremely simple. You just write down like a plane wave and also some all possible like permutations of the momenta. And because of this, in this ansatz, the states are parameterized by these momenta of the particle, or often called rapidity of the particles. And so this is the step one. And in the step two, we just impose that this is an eigenstate of the Hamiltonian that I just wrote in the previous slide. And remarkably, if you just impose this condition, you can immediately determine so this factor, which was just some unfixed parameter in this ansatz, to be of this form, where these ui's are related to the moment of the particle in this way, and it's often called a rapidity variable. And in addition, you discover that momenta of the particle cannot be arbitrary, and it needs to satisfy the equation like this. And so this equation, so if you forget about this S part, then it's just a standard periodicity condition for the plane wave. And if you include this S part, it has a nice physical interpretation. So the physical interpretation is that you pick one excitation and moves it around the spin chain side, then from the propagation, you get this factor. And however, because the theory is interacting, in addition to the propagation, you get additional phase factor, which comes from the scattering of different excitation. And this is, so from this interpretation, this has nothing but the S matrix. And basically this Bethe equation is just a condition for the periodicity of the wave function in the presence of interaction dictated by the S matrix. And thirdly, once you determine the set of momenta by this equation, solving this equation also tells you that the energy of the state is just given by the sum over energy of individual Magnum states. So this is how Bethe ansatz works in practice.
Shota, can you just clarify?
Yes.
The S is, I mean, it's a very simple S matrix, right? I mean, it only depends on the two momenta. Maybe you should draw you should explain that. That's the integrability hypothesis, right?
Yeah, sorry. Yes, right. So okay, indeed. Okay, so this is indeed, as Clayton pointed out, like if you look at this wave function, then I said like it's basically just a sum over permutation, but on top of the sum over permutation, I made a very like a restricting assumption that the coefficient in front of the different plane waves are just given by a simple product of some simple factors, which only depends on two momenta. So in general, if you were to write down an ansatz, so this and this can be completely different, and it doesn't have to be related in this way. However, in this ansatz, I assume that everything is given in terms of this two-body, what's called two-body S matrix. And the reason why, well, first of all, like if you write this ansatz, it works. And the reason why it works is that because of the integrability, if you consider multi-particle scattering, so this theory has a lot of symmetry. And if you consider the multi-particle scattering, like a 3 to 3, then by acting some symmetry generator, you can move the trajectory of the particle. Let's say like we are considering the scattering of wave packets. And by acting some linear combination of the symmetry generator, you can move the trajectory of the particle and then convert this into this kind of scattering in which only two of the three particles scatter at one space-time point. And so this is basically the reason why you can you can write all these factors in terms of like product of what's called two-body S matrix. And on top of that, you can also use a different set of generators. So this is one set of generator alpha SQS, and this is a different set of generator alpha SQS prime. Then you can convert this into a different picture like this. And the equality between the two is what people often call Yang-Baxter equation. And you can also try to determine S by solving this equation. But here, I didn't use that approach. I just imposed the eigenvalue condition. Okay, so this is how the Bethe ansatz works in this simplest spin chain, which is Heisenberg spin chain. But of course, in n equals 4 supermills, there are like a lot of more operators than the one that I described here. And in addition, of course, this story was just for one loop, and then you can ask what happens at higher loops. And people analyze this problem also at higher loops, just doing the perturbative computation and then mapping to that spin chain. And remarkably, in all the examples people studied, the relation to integrable spin chain, I should have said the integrable spin chain here, persists even at higher loops. Although there are several new features, for example, if you go to higher loop,
by higher loop, do you mean higher orders in 1 over n?
Sorry, this is like a higher order in in lambda.
Lambda, okay, thank you.
Yes. So, and there are several new features. For example, if you go to 2 loop, then you have next to nearest neighbor interaction. And if you go to 3 loop, you have next to nearest neighbor interaction. So basically, n equals 4 supermills generates various complicated long-range spin chain, which is still integrable. So in that sense, you can also view n equals 4 supermills as a kind of generating theory for various interesting long-range spin chain, which is integrable. And also there are like some finite size effects that you need to worry about if the range of interaction exceeds the length of the spin chain. But there are also ways to analyze this. And integrability still survives in the presence of such finite size effect. And the basic picture is that, so this spin chain, on the, which you discover from the gauge theory side, you can also study some limits. So originally the limit was studied by, Berenstein, Maldacena, and Nunes, so the famous BMN paper. And they discovered that in this, basically, if you increase the coupling, this spin chain just becomes 1 + 1 dimensional sigma model with AdS target space. So this is also like one manifestation of AdS CFT duality. So instead of directly talking about gauge theory and quantum gravity, here we are seeing the manifestation of the AdS CFT correspondence at the level of 1 + 1 dimensional system. So you get the spin chain from gauge theory and the sigma model from the string theory. And by now, so they're having like a lot of progress since 2002. By now, we have a reliable and efficient method to compute a spectrum at finite lambda, which is called quantum spectral curve. So I'm not going to talk about what this quantum spectral curve is in this talk, but let me just give you some highlights of the result. So this is the result for 11 loop anomalous dimension of the Konishi operator. Of course, this was predicted by this efficient method called quantum spectral curve, which is basically like some Riemann-Hilbert problem. So you can convert all this problem into some kind of Riemann-Hilbert problem for a set of functions. And by solving it, you can generate this analytic data. Of course, like people cannot really verify this because no one can do this 11 loop computation. But this is an interesting prediction for the 11 loop anomalous dimension. Another thing people can do is to numerically study quantum spectral curve or related system and make a plot for the dimension of this Konishi operator from weak to strong coupling. So roughly speaking, these dots are numerics, which is obtained by integrability. And this is the prediction coming from analyzing string worldsheet. And this is roughly coming from the gauge theory. And you can see that this exact result nicely interpolates between integrability and string. So in this plot, the string seems to be doing rather well, but if you look closely, then you start seeing deviation between string and exact answer at weak coupling. Okay, so that was the story about the dimension of the operator, which basically governed the 2-point function, because n equals 4 super Mills theory is a conformal field theory. And as I said, the most advanced method was the quantum spectral curve, and that was achieved in 2013. And soon after, people started analyzing the next important question or important quantity, which is the 3-point function, because n equals 4 super Mills is conformal, so that once you understand 2-point function, the next question is the structure constant. And so far, the most advanced method for this class of operator is the one proposed in 2015, which is based on the idea that 3-point function corresponds on the string worldsheet a pair of pants geometry. And the basic idea is that instead of studying pair of pants directly, you decompose pair of pants into 2 hexagons, and then you can actually determine the contribution from each hexagon from integrability. And if you want to recover the full 3-point function, you just need to identify these edges, which amounts to inserting all possible states here and summing it up like this. However, the problem here is that although we can determine individual objects at finite lambda, this sum is practically hard because it in the end involves infinite sum and infinitely like coupled integrals. And so this was the status around 2015. But in today's talk, in the rest of the time, I'm going to talk about the new development, which happened in 2019, started to happen from 2019. And we discovered that there is actually a new class of correlation function for which this sum, infinite sum, can be actually performed analytically, or sorry, explicitly. Yes?
Shota, before you go on, can you explain in a little bit more detail what kind of object is the hexagon? So it's the thing that you're trying to sum there. So right. What is it from the point of view of the worldsheet CFT? It's some boundary. What we have some boundary conditions, and we're computing what?
Yeah, that's a good question. So I don't have a very clear answer from the boundary the worldsheet CFT point of view, because so if this were the boundary states rather than like a perturbative string, state, which is described by the vertex operator, then what we are doing is very simple. We have boundary here, and we are just like summing up all possible open string states appearing here. Mm-hmm. However, these states are actually not the boundary states because it's supposed to be dual to the single trace operator, which should correspond to some vertex operator on the string worldsheet. So I don't have a clear answer from the worldsheet CFT point of view, but there, at least here, there is some at least formula that you can write down, and then that reproduces the answer from the gauge theory.
Is this like some KLT type relation?
Yeah, so it has a flavor of KLT, but for example, if you consider instead of like a 3-point function of single trace operator, if you consider 3-point function inserted on the Wilson loop, then we just have one hexagon, and that is due to some kind of open strings like a 3-point function on the worldsheet in the AdS. So in that sense, it's a bit like KLT, but there is no like. Yeah, yes.
No, go ahead.
No, please ask.
So what's the difference between the sides of the hexagon that have a dot and those that don't?
Right. Okay. So yeah, there is a very important difference indeed. So let me see. Right. One thing is that so on this edge, we are always having some state with finite size because it's basically given by a length of the spin chain, or more precisely given by the R charge of the state. So this is always finite size. So these lines are supposed to be finite size, but this line is supposed to be infinite size. And in fact, when we sum over state, we basically like a sum over excitation whose momenta runs from minus infinity to infinity. And if I go back to this like a Clay's question, then that is related to the fact that these states are really actually like a vertex operator, which is point-like. And if I try to measure the lengths between two vertex operator, it's kind of infinite.
Okay.
So that's one difference from like a boundary state.
So rather than being a finite pair of pants, it really is a
right
point like 3-point function.
Yes.
Okay.
Yes.
Thank you.
Okay, thanks for the question. So, okay, so let's now talk about the new development. So the new development is that the people found that there are actually a class of correlation function for which this sum or a sum and integral can be performed very explicitly. And there are basically, well, several of them are already discussed in the paper. And one is the 3-point function of 2 determinant operators and 1 single trace operator. And the second one is the 2-point function of Wilson loop and single trace operator. And the third one is the single trace operator in the presence of codimension 1 defect. And all these examples have 3 common features. First, all of them involves 1 single trace operator. And second, as I will explain, at weak coupling, you can describe it in terms of overlap between matrix product state and the energy eigenstate in the integrable spin chain. And on the other hand, on the string theory side, or at finite coupling or at strong coupling, all these are described by some overlap between closed string state and the boundary state. So now we really have a boundary state. And this boundary state is, of course, like from the string theory point of view, is related to the D-brane. And also from the condensed matter point of view, or like a 1+1 dimensional point of view, this is basically generalization of what's called G function introduced by Affleck and Ludwig. So they basically studied a case where this state O is ground state. But for the application of AdS CFT, we also need generalization for which this is excited state. Okay, so now in the rest of the time, I'm gonna explain all these 3 features in this first example, determinant, single trace operator. And this is basically the setup of the 3-point function, or details of the 3-point function that I'm going to consider. So I consider 2 determinant operators. So determinant operator is yet another class of gauge invariant operator you can define in n equals 4 supermills. And we take 2 of them to be conjugate, and they are actually half BPS. And then the last one is a generic non-BPS single trace operator. And the goal is to compute this at finite Hooft coupling in the large N limit. Okay, so now let me just explain why this object can be interesting. So let me just give you 2 answers. So why we want to study determinant, or why studying determinant is interesting. So the first reason is that determinants are in some sense analog of baryons, not precisely. But, so the reason is that in the large N QCD, roughly speaking, the baryon is just given by this expression, which involves 1 epsilon tensor and then like an n quark fields. In n equals 4 supermills, because all the fields are in the adjoint representation of the gauge group, we do not have the direct analog of the baryon. Instead, we have this operator. So because we have 2 indices, each field has 2 indices, and that is nothing but a determinant operator. And the common feature between these 2 operators is that both of them are actually difficult to analyze using the standard large N expansion. And it's actually nice to develop some new techniques, because once we develop techniques for n equals 4 supermills, maybe we can use some of them for studying a bit more realistic situation, which involves large N QCD and baryons. And another reason why it's interesting is that it can provide some very ideal local prob of AdS. So the reason is that determinant operator corresponds to D-brane, which is very heavy in the large N limit, but still does not back react the geometry. So this is basically the reason why it does not back react. So the dimension of the determinant operator is of order n, where n is the rank of the gauge group, which is much larger than 1. So this means that the wave function of the determinant operator is very much localized in AdS. So it goes along the geodesics, and it behaves like a classical particle. However, because n is much smaller than n squared, so it's not heavy enough to back react the geometry. So in this sense, if we want to analyze some kind of like a geometric feature of the AdS spacetime, determinant operator can actually provide a very ideal probe, nice probe. And by the way, yes. By the way, this particular determinant operator is what's called, that we study here, is what's called giant graviton, and discussed in this paper, for instance. Okay, however, I should also emphasize that studying determinant operator is indeed hard. And the reason can be summarized in this picture. So let's consider or contrast the perturbative computation of two-point function in the plane element. So if you consider the single trace two-point function, so at leading order, at tree level, you just do the planar with contraction. And if you start including interaction like gluon exchange, then you get one extra hole. So you get a factor of n, and because you use the two vertices, you have like a GML squared. And this nicely combines into the Hooft coupling. So that's why the Hooft coupling makes sense in the plane element. On the other hand, if you consider determinant, because determinant is basically defined in terms of epsilon tensor, there is roughly speaking no ordering among these fields contained inside this one determinant. So if you were to draw some like a gluon interaction vertex or gluon propagator, then you can actually like connect any of these two lines, which comes from the propagator of like a determinant operator, fusing the determinant operators. And that gives you this combinatorial factor of n minus 1 over 2. And as you can see that if you take the usual large n limit, it blows up because this one nicely combines into the coupling, but there is remaining n, which blows up. And if you do the higher loop computation, it actually gets worse. So like a leading order, if the leading order is order 1, the next leading order comes with n, the next to next comes with n squared. So you might say that there is no hope to do the analysis in the large n limit or planar limit. However,
sorry,
yes.
This is a BPS. These are BPS operators, right? Half BPS?
Yes, indeed. Yeah. So for the BPS operator, this particular problem doesn't exist, but this combinatorial problem exists, for example, if you consider 3-point function with extra non-BPS operator. However, I should say that, okay, however, this problem was already addressed in the 80s, and people argue that from various grounds, from various like physical arguments, that this actually exponentiate in the large n limit. And what you actually need to look at is the exponent. And that is the one that has the nice expansion in terms of the Hooft coupling. And indeed, you can actually verify this behavior in simple model like 2-dimensional Yang-Mills. But this exponential behavior basically suggests some semi-classical description because it comes with a large factor, which is n. And the natural question to ask is, what is the semi-classical description? And the answers are known in some effective description. For example, in the usual large n QCD, it's often given by skyrmions in the pion effective theory. Or in the context of AdS CFT, as I said, it's given by the d-brane in AdS spacetime, which becomes classical in the large n limit. However, it is not so easy to get this direct semi-classical description directly from like a UV Lagrangian. But for n equals 4 supermills at weak coupling, using some idea from, well, simple ideas basically using some simple idea from matrix model, we can derive the exponentiation exactly and obtain some semi-classical description. And the final result has some nice, interesting connection to the matrix product state. And that's what I would like to talk about next. So this is the topic of the next bullet point. Okay, so the idea is to develop some kind of collective field approach, which describes the determinant operator in the large N limit. So the basic idea is to derive some dual action by a sequence of integrating in, out, in, out. And this idea was used a lot in the matrix model, but not so much in the field theory. And you can also understand it in terms of graph duality, which I mentioned, and also related to some interesting but not widely known ideas explored in the past. And I'm going to mention one of them. So let's do the analysis. And to simplify our life, I'm going to describe it at tree level. So actually everything is super simple. So the idea is so let's consider like a correlation to be slightly more general. Let's consider the correlation function of M determinants and one single trace operator. And we write it in the path integral. And determinant operator is defined in this way. And in order to preserve this supersymmetry, this direction, this polarization in the R symmetry direction must be null. But anyway, the details of the form is not so much important. And now, so because we have a determinant, the next step is to just rewrite determinant using zero-dimensional fermions, like this. So this is, of course, like a standard trick everyone knows. And now, so this fermion, I should mention that this chi k is the fundamental of UN, whereas chi bar is anti-fundamental of UN. And now, if everything, after this rewriting, everything is in the exponent. And in particular, if you look at the scalar field phi of n equals 4 supermills, the action is quadratic because it's tree level. And then determinant gives you just linear term. So you can basically integrate out n equals 4 supermills by completing the square and do the integration, path integral of phis. And if you do so, then in the end, you end up with replacing phi with this S. So this is relevant if you consider like an insertion of extra operator O, which is given in terms of phi, for instance, like let's say we consider some like a trace of phi to n. Then after doing this integrating out procedure, you are going to replace this expression by replacing this expression, which you can obtain from replacing phi with this S, which is bilinear of fermions. So this is just a standard thing that you get from the Gaussian integration. So now, yes.
Why is it just Gaussian and phi? In the end?
Okay, so yeah. So let me just say that.
Is it completely conservative at coupling or?
So no, right now we are doing it at tree level, but large N limit. And you can also perturbatively include correction. And there is a systematic way to do so. But I should say that this, of course, you cannot do this directly at finite coupling. And then to understand finite coupling behavior, we need to use integrability. But this tree level analysis gives us some insight. So now, after doing this, we get this action because so we are still left with fermion integral, but now an important point is that now we have a quadratic action of fermion, and we do the standard trick of doing the Hubbard-Stratonovich transformation by inserting some meson field, which is rho ij. An interesting point about this rho ij is that this rho ij is actually M times M matrix, where M was the number of determinant operator that we inserted. But basically the rest is very simple. We have this action, and now, as you can see that this action comes with a factor of n, so you can already see something becoming classical. But then we still need to integrate out fermions, but that is easy because it's Gaussian. So then if you do that, we get some effective action of rho, which involves this term and the determinant of this term, which also scales like n. proportional to n. And then what you need to do is to find the saddle point of this action. And in addition, if you have extra insertion, you also need to, this extra insertion also fills some this extra insertion, just to remind you, is given by this field S, where S was the bilinear fermion. So when you do the fermion integral, you also need to do the weak contraction for this operator. And for this weak contraction, the propagator is basically given by this inverse of this rho. And this rho, in the end, is going to be evaluated at saddle point, and that is going to give you the answer for this expectation value of the scalar, the single trace operator. So this is a little bit technical, but straightforward, but technical part. So as I said, if we want to evaluate this O, we basically first replace this phi with the S, which is the bilinear fermion. So you get this kind of expression if you start with a single trace operator like this, where the gauge indices are contracted in this way. And then we are going to do the weak contraction of fermion using this action. And when you do the weak contraction of fermion, you can see that if you contract the neighboring two fermions, you get delta BB, which is proportional to n. Whereas if you do a different weak contraction, you don't get this factor of n. So in the large n limit, you are basically forced to contract the neighboring fermions, and that is going to, each contraction gives you this propagator, which is the inverse of rho. And interesting thing is that this whole expression nicely combines into some trace of some matrix, classical matrix, some C number matrix. Because in the end, rho is to be evaluated at the saddle point. So this expression actually looks like an original single trace operator expression, but there are several important differences. So in the original expression, this trace was taken over n times the n matrix, where you take n to be infinite in the large n limit. Whereas in this expression, you are taking the trace over m times, so each matrix is m times m matrix, where m is the number of determinant operator you inserted in the beginning. So and another interesting property is that you can also rewrite this expression. So this gives you the 3-point function in the presence of determinant operator. You can also rewrite it as an overlap between the state O, spin change state O that you write down, which is due to this operator, against this matrix product state. This is just like a simple rewriting of the same expression. But this basically tells you that if you were to map all the computation to the spin chain computation as we did previously, then the computation reduced it to the overlap between the matrix product state and the Bethe state, and the spin chain eigenstate. And I should also mention that there is some emergent m times m structure. And this reminds us some Champeyton-like structure, because we know we inserted m determinant, which should correspond to like m d-branes. And in the end, we are finding m times m structure. So it really reminds us some like a d-brane physics. So there is some gauge theory description of this whole process. So the idea is to realize determinant operator as an intersection between stack of n d3 brane, which creates n equals 4 sup m mils, and extra probe d3 prime brane. And using this description, we can actually explain the whole step that I explained in the previous slide in this way. So the idea is that now we have this D3 and D3, there is some fermion open string stretching between two of them, between this and this. And that is going to give you the fermions that we introduced. And after introducing fermion and you are integrating out this n equals 4 degrees of freedom, you basically replace this stack of D-brane by a curved geometry. And in the end, you get this kind of connected D3 brane and probe D3 brane in AdS spacetime. And the rho that we introduced after Hubbard-Stratonovich is really like meson in which is made out of two fermion, two open strings. And another interpretation is that you can also interpret this as a graph duality. So the idea is as following. So originally we had determinant operator, which creates some complicated contraction pattern. But in the step 1, we introduced fermion and rewrote the determinant as a Gaussian integral of fermion. And in terms of graph, or like a double line notation, this is like introducing extra line here and viewing this as a fermion. So here, like I have something which is fundamental, and here we have something which is anti-fundamental, which is in line with what we saw. And in the step 2, we integrated out n equals 4 supermills, and that from this picture, you can clearly see that that creates this quartic interaction of fermions. And in the step 3, we integrated in this extra field, which is a meson, and to resolve this quartic interaction. So in graphical picture, we arrive at this expression. So if you superpose the original picture to the new picture with the new picture, then you can see that in terms of graph, the original graph becomes the dual graph. So this is the reason why I said like this is related to the graph duality. And in fact, this graph duality was already discussed by Gopal Kumar in a slightly different context, which is the connection between non-critical minimum string and the matrix models. So it is known that the non-critical minimum string has 2 different matrix model description. One is given by double scaling limit of one matrix model, and the other is given by what's called conservation matrix model. And he pointed out that you can go from here to here, basically doing this graph duality manipulation, and you can also interpret it in a graphical way. And what we did here is in some sense like some slight small generalization of what they did in this context to n equals 4 supermills. So of course, if you had n equals 4 supermills, the natural dual description is like a string theory or a string field theory in AdS. But and this duality, this part of the duality is the analog of the duality between one matrix model and non-critical minimal string. But this field theory of rho is in some sense a bit like this third part. And so of course, like this doesn't describe the full sector of n equals 4 supermills, because I only talked about the correlation function involving determinant operator. An important question is whether one can kind of generalize this kind of idea to the full sector of n equals 4 supermills to find this yet another dual description, which is the analog of the conservation matrix model for n equals 4 supermills. So this is to a bit.
So are you relying on some sort of localization or something? Because I mean, the fermions, for instance, were what? Just 0-dimensional Grassmann variables?
Okay,
or were
so
there
in
actual fields in some field theory?
So in this computation, I didn't rely on any localization, but of course, like I did the very 2 simple computation, which is tree-level computation. And so
But I guess I'm so you're starting off with D3 brains, right?
Right.
Both the background D3 brains and the probe D3 brains.
Right.
So they're both, the degrees of freedom on those are field theoretic, but it looked like your integrals were finite dimensional integrals.
Yeah, so I think like what's happening here is that like this, from the point of view of this stack of D3 brain, like what you see, especially in this like field theory limit, is this open string, but like localized at the intersection point.
And that intersection is point-like?
Yeah, and the intersection is point-like.
Okay.
Because we are talking about the local operator. Okay, so actually, I just wanted to mention that.
Just one more question. So, I mean, the procedure is very pretty and it looks very straightforward in this case. So this is, but
right.
If I replace the determinant of a scalar, a fundamental scalar, with some composite scalar, or some scalar operator in the theory, at tree level, can you still go ahead and follow all the steps and end up with some expression?
Yeah, well, yes. So you can do it, but then like the idea is to rewrite those operator in terms of determinant operator. That's the only way I know how to do it.
Okay.
Because, for example, if you consider slightly generalized object determinant x minus z, where x is some free parameter, then if you expand in powers of x, you can get various different operators. And you can also consider one of a determinant, for instance. And combining all of them, you can get a huge operator as well. Okay, so I guess.
Can I ask you a question?
Yes.
The inverse determinant operators, what's their interpretation in AdS/CFT?
Right. So the inverse determinant operator, so determinant x minus z roughly corresponds to, so both are D3 brane. So this is D3 extending inside S3 of S5. The inverse is again D3, but it's extended inside S3, inside AdS5. Okay. All right, so let's proceed. So how much time do I have? Like a 10, something like 10?
Yeah, we started late.
Yeah, okay, so let's say 10. So anyway, this next part is anyway very technical, so I'm not gonna go into the details. So as I said, if you do this trick at tree level, then the computation reduces to the overlap between the matrix product state and some eigenstate, energy eigenstate of the spin chain. And this object was studied a lot in the recent past in the statistical mechanical literature in the context of quench dynamics, because they wanted to start with some matrix product state, which is short range entangled, and wanted to study how it evolves under the time evolution. And in order to analyze it, the basic ingredient that you need to know is this overlap between matrix product state and energy eigenstate. And so they have a lot of results. And in particular, for the case that's relevant for us, there are two interesting features in the result. First of all, this object, the overlap, obeys some selection rule. And in particular, it is non-zero only when the state is paradismetric, by which I mean, if you have a state with downspin excitation with momentum P1, it also contains a downspin excitation with momentum minus P1. And secondly, the final result is given by some nice ratio of determinant. The details of the form is not relevant, but this is determinant made out of some logarithmic derivative of the Bethe equation. So the first feature of the selection rule suggests some hidden symmetry. And the second feature suggests some kind of like a one loop fluctuation around some on-shell configuration. And the nice thing about using AdS/CFT or string Worldsheet picture is that both of features can be explained very naturally. So let me just remind you that what is the holographic picture? In the holography, you have some determinant operator, sorry, D-brane, which is created by the determinant operator, and there's a closed string attached to it. And from the Worldsheet point of view, it's given by some overlap between the boundary state and the closed string state. And now, and then like we can study like how the Worldsheet dynamics, well, how the boundary affects that Worldsheet dynamics, the dynamics on the Worldsheet. So now the first thing to note is that, so we observe that so only parity symmetric state has non-zero overlap. So if I were to draw a picture, so here is a boundary or matrix product state, and then we are like inserting some excitation, and this excitation needs to be parity symmetric. And now we are on the Worldsheet, not on the spin chain, so we can freely flip the space and time, which was not possible if you stick with the spin chain picture. But in this like a rotated picture, you see that this process is nothing but the reflection process, in which like a particle of momentum U1 and U2 gets reflected to minus U1 to minus U2. But I should also say that this is a very particular reflection process in which particles only changes the sign. And in this reflection process, you can clearly see that this combination is preserved, which means that there is some hidden charges preserved by this reflection process. And this is indeed the characteristic feature of what's called integrable reflection, studied by Gosho and Zamolodchikov. And if you assume the existence of this charge, and then run the same argument as I presented before for the S matrix, you can convert this reflection process into two different reflection processes. And because they are related by the symmetry generators, they must be equal. And that gives you what's called boundary Yang-Baxter equation. So basically, the upshot is that this selection rule that we observed at weak coupling, if you translate that selection rule to finite coupling using this Worldsheet picture, it basically tells you that this boundary state is what's called integrable boundary state. And once you know, or once you accept that it's gonna be described by integrable boundary state, then the problem reduces to determining like a one particle reflection amplitude, because in the end, everything reduces to one particle reflection amplitude. And you can do it by imposing several consistency conditions, which is often called integrable bootstrap. One of them is what I just explained, boundary Yang-Baxter equation. The other ones are symmetry of the problem. And also there is some what's called boundary unitarity condition, which I don't have time to describe. But the point is that these conditions were actually enough to completely fix the reflection matrix. And in the end, the result has a nice doubling interpretation. So in the end, like, so this reflection process is related to this scattering process on the worksheet. And this, because we know the scattering process on the worksheet, thanks to the works in the previous literature, we can actually determine this completely. So now, once you determine the reflection process, then reflection amplitude, then we can actually go ahead and compute this object. So the idea of how to compute this object is to use the channel duality, which is very common in string theory, string worldsheet. So the idea is to consider a cylinder partition function in the limit where this length becomes infinite. And in this limit, if you expand the cylinder partition function in this channel, then you get the sum over state. And in particular, when R is very, very large, this sum is, for example, dominated by the ground state. And that case is the particular case studied by Affleck and Ludwig. On the other hand, you can also study this from the open string channel. But now what you need to do is to study the thermal partition function at inverse temperature L, in the limit where the spatial distance becomes large. And in this limit, the sum over open string state, which takes of this form, can be replaced by a sum over density of particles, because now we are taking infinite volume limit and we have a lot of particles, so you can replace the sum with the path integral of density of particle. So this is what's called TDA, thermodynamic Bethe ansatz. And then the next step, and this effective action is basically determined by the reflection amplitude that we determine using the bootstrap analysis. So we feed the answer from the bootstrap and determine this effective action. And once you determine the effective action, you can just evaluate this again using the saddle point trick. And if you compare these two expressions, you see that like a different saddle basically corresponds to different states in the closed string channel. And the saddle point equation is what's called thermodynamic Bethe ansatz equation, which you can solve. And if you analyze one loop fluctuation around the saddle point, so because the saddle point itself gives you this exponential factor, which just gives you the energy of the closed string. So in order to determine the prefactor, you just need to compute the one loop determinant. And if you do the computation, then it gives a complicated but nice answer. So the final answer of doing this computation consists of two parts. One is given by some kind of finite product and finite determinants, which looks like the represent expression that we got from the weak coupling or tree level. And the other part is very complicated, but similar looking structure. But the important difference here is that here you get functional determinant, which is Fredholm determinant, And the basic reason why you get the functional determinant is because you are doing the one loop fluctuation of the path integral. And this looks complicated, but it turns out it becomes one if you take the weak coupling limit, for example, tree level of n equals 4 supermills. And this indeed reproduces and generalizes the weak coupling answer, and you can explicitly even reproduce the like a higher loop correction. And another thing to mention is that although we studied this for this I explained this for a particular problem of a determinant single trace operator, the same technique can be basically applied for other quantities, which also involves D-brane in the holographic picture. And I just listed several of them here. But one important outcome of analyzing various different contexts is that there is actually one intriguing observation. So as I said, at weak coupling, the computation reduces to the overlap between the matrix product state and the spin-chain eigenstate, whereas at finite coupling, you get some boundary state, which is on the string worldsheet. And what's interesting is that in all these examples, the bond dimension of the matrix product state that you get at weak coupling is exactly equal to the number of so-called boundary bound state. So basically what happens here is that you analyze the reflection amplitudes, and it turns out the reflection amplitudes sometimes have poles. And this pole signifies the existence of some kind of boundary state in which like some particles are localized on the boundary. And if you count the number of boundary bound states in various example here, and that precisely matches the bond dimension that you see at weak coupling. So this basically suggests that although this computation was done at tree level, already this kind of knows the worldsheet degrees of freedom. So worldsheet degrees of freedom can be seen already at weak coupling. And by the way, this D was 2 for n equal for determinant operator because we had 2 determinant and 1 single trace operator. And for D instanton, D is 1. And for the Wilson loop, D is infinite. And for the domain wall, you can take any integer values depending on the situation that you study. Okay, so let me just conclude now. And so the summary is that now there is a new class of computable correlation functions in n equals 4 supermills. And there was interesting connection with statistical mechanics, like matrix product, state, and a G function. And the future direction, there are like several things that we can hope to do. One question is one more field theoretic. So it might be interesting to try to apply these techniques to other setup, or ABGM is just like a boring generalization, but maybe for like a tensor model or Chern-Simons vector model. And another thing interesting direction is that here I said there is some connection to what's called open-closed open duality proposed by Gopal Kumar, but obviously what we analyzed here is very limited because we are just looking at a particular class of operators, which is determinant. So it would be nice to generalize this idea to more general class of operators and also to find out field theory at finite coupling rather than tree level and including perturbative collections. Finally, in the previous slide, I mentioned the interesting observation that bond dimension of matrices in the matrix product states is exactly equal to the boundary bound states of the string worldsheet. So this already allows you to see kind of edge of the worldsheet, which is localized at the boundary. So it will be nice if we can extend this observation to the bulk of the worldsheet and see what's living in the bulk of the worldsheet from the gate theory. But of course, this is more like a speculation. Okay, so that's all what I wanted to say.
I got a couple of quick questions.
Yeah, so we could go back to your expression with the exponential and so on. This one, yeah.
This one,
no,
okay, okay. Sorry, this one?
One more, here we go. So is the last, whoops.
Oops, which one? This one?
One more forward.
One more forward. Okay.
Yeah. So am I understanding correctly that the last factor is what is this, is basically the exponential of the d-brane action, or is it?
Oh.
Is this the thing that's like e to the n times f of lambda?
So actually, the answer is no. So this is directly computing this disk with one puncture from the string worldsheet point of view. So it's not exponentiated because we are looking at the like a overlap between the boundary state and the closed string state, which is precisely like a disk with one puncture, where puncture is a vertex operator.
So what's the interpretation of the last factor then from string point of view?
So from the string point of view, let's see. So this, okay, so let me just say that this part is actually some logarithmic derivative of the reflection amplitude. So this is like so this one. So in some sense, this is more like a computing the phase shift coming from the reflection. So it's really like worldsheet dynamics rather than space-time dynamics.
I see. Okay, thank you.
Can I ask a question? In the instanton case you have here, is the analogous picture the overlap between the instanton boundary state and the closed string state, or?
Yes, exactly. That's what we are studying now. So the idea is that you can compute this for a fixed moduli. And then if you want to compute a 4-point function, you multiply 4 of them and then integrate over the moduli. And unfortunately, like this moduli integral is not coming from integrability, it's beyond the worldsheet. So we need to kind of partially guess, and we also need to kind of rely on the comparison with some localization answer. So this is a part which is not super rigorous and which we don't have a full control right now.
Usually, is this like the measure for the modular integral?
Yeah, this is a measure for modular integral, but you know, like there is also some like this factor, and right. it's just hard to like say that we understood everything.
Because usually the measure comes from exponentiating like some annulus diagram. Right?
Yeah, that's also true indeed. Yeah, that's a good point.
If there's an analogous picture,
right? And I should say computing annulus is hard for using it. Yeah, at least now.
Thank you.
Okay, if we don't have any more questions. Stop recording. All right.
I knew it was Halloween cake.